engineer in Valley Water's recycled and purified water unit. He currently leads the reverse osmosis concentrate management program, which is no small undertaking. Obviously, this is a very growing area with Valley Water. I mean, basically looking to more than double capacity. He gets, what keeps him up at night? Worrying about brine, probably. What to do with it, and as a byproduct of the reverse osmosis and some of the filtration. So he oversees the research and special projects pertinent to the expansion of recycled and purified water. He has over 25 years, he looks very young, but 25 years of experience in water and wastewater, stormwater, recycled water. How you slice it, it's amazing. And chemical manufacturing. He has a MS in engineering with a concentration in water resources, and is a licensed chemical engineer in California and an environmental engineer in Nevada. And I asked him to kind of give a roundup since he is so much involved in, kind of innovation and new technologies, pilot projects at Valley Water, to give kind of a roundup of that with a special attention to brine. So I will hand him the magic pointer with the green. Take it away.
All right, great to be here. Thank you everyone for your attention. Thanks Dennis and Jennifer for having me here. Medi Sinaki, Recycle and Purified Water Unit, Valley Water. So you heard from Dr. Ashtrop earlier, around 1 o'clock I believe, about Valley Water and the projects we are doing with emphasis on purified water and water recycling. So what I'm going to present here very quickly, I know we are kind of running out of time, but I just want to do a roundup of what we have been doing to address contaminants, brine, and technological challenges that come with water purification and water recycling. So with that, we first go talk about Valley Water a little bit. You guys know we're a large agency. We serve most of the 2.5 million people who now live in Santa Clara County. We work with 13 retailers. We have about 5,000 wells to manage, a bunch of other stuff. So we're a pretty large agency. But one of the areas that we are focusing on and have been focusing on is water recycling and increasing our production of potable reuse with a target of 24,000 acre-feet a year by 2028. It's a very challenging target, but we are confident we can hit it. So the journey really started many years ago. So City of San Jose and Santa Clara and Valley Water had the vision of working together and building the first ever large purification facility in Northern California known as Silicon Valley Advanced Water Purification Center. The purpose of this was to act as a demonstration facility, educate public, and at the same time produce up to 8 million gallons a day of purified water in order to enhance the quality of the recycled water that South Bay Water Recycling System of the City of San Jose serve to their clients. Because of the TDS, or total dissolved solids, in that recycled water, some of the clients were not taking the water because for cooling towers and redwood trees, etc., the TDS needs to be roughly around 550, and the TDS of the recycled water was roughly around 830. So by building this facility and blending the 8 mgd, or million gallon per day, of the water that it produces at about 40 TDS with the 830 roughly TDS of the South Bay Water Recycling, you're able to drop the TDS to roughly about 550, hence making it more suitable. So in addition to that, which kind of ushered in the whole thing about potable reuse and water purification, we also started looking at countywide water use master plan, which started roughly about 7 years ago, looking at various ways to work with the cities around the Bay, Palo Alto, San Jose, to build additional facilities for water purification. One of them that is being planned right now, as again earlier alluded to by Dr. Ashtrop, is the 10 MGD facility that would be built in Palo Alto. So this facility would be a full advanced purification center with reverse osmosis, microfiltration, and ultraviolet and advanced oxidation processes to produce the water that is close to drinking water standards, but it's going to be used as indirect potable reuse. And the byproduct of that would be RO concentrate or brine. In addition, in order to make sure that the water that you are serving is meeting the regulations and suitable, you need to address contaminants and work with the regulators, etc. So this whole thing brings us to having Valley Water investing lots of resources in looking at technologies for saving energy, for example, looking at technologies for reducing the amount of contaminants in the purified water, addressing the RO concentrate management issue. So our journey into research continues, and we are involved with multiple number of institutions. I'm going to just give you a few examples here. One of the very prestigious institutions that most of you know about is Water Research Foundation. So their role is, they're federal, and their role is to invest in research and provide avenues for agencies, academia, etc., to work together to identify solutions for improvement of water quality, addressing human health, safety of water, energy savings, etc. And they provide various opportunities for grants and joint ventures with utilities and academia. So we have been involved in that, and we have been participating in Water Research Foundation projects. And here are a few of them that I wanted to kind of point out. There are multiple numbers that we don't have time to go through, but these are some of the highlights of the ones that we have worked on. For example, 5049. This was a recent project we completed. It looked at producing highly purified water and blending it with drinking water that comes out of the regular standard drinking water treatment plant, and seeing what kind of impact you will see. So through this research, which we was a joint venture with Water Research Foundation, Crollo Engineers, a large consulting company, and a couple of Southern California sister agencies, we looked at this. We basically brought pilot skids. We installed it at one of our facilities with Sona Pump Station, and we ran various tests, very rigorous, took about a year and a half, lots of resources. And we found out that there are benefits to this. For example, at certain blend ratios, you start saving chemicals that otherwise would be needed at higher levels at a regular drinking water facility. And at the same time, we found out that there are optimal blending ratios that could reduce the energy that is required for mixing and doing other things to water before it becomes suitable to meet the drinking water standards. So it really was a telling research that we did, and the outcomes of it have been published, and they're going to be presented at various venues. Another research that we did in joint format with City of Palo Alto and Crollo Engineers and a couple other agencies, Ventura, City of Ventura down south, was looking at source control and using sensors throughout the collection system, monitoring for contaminants, and then modeling the existing source control programs of various components of it to see whether it could be enhanced to meet the regulations that are coming up for direct potable reuse under enhanced source control program. Again, this allowed us to model the source control program, conventional source control program for Palo Alto, and identify areas where improvements could be made if we were to convert it to an enhanced source control program. Palo Alto currently has a very robust source control program that meets the regulations, so there is no issues there. But if we were to enhance it to meet the future DPR requirements, DPR is direct polar reuse, which the regulations are being finalized in a few months. So that showed that model that could be used to change that conventional system to an enhanced program. Another research that we did was looking at using data for real-time decision making and using various tools to crunch data, look at the critical control points in the treatment systems, and being able to use data to be more reactive to offsets of specs in a treatment system. This, again, would allow a safer way of operating future facilities and would feed into energy savings, less operator errors, and safer water for the final user. So the model that was used through this process can be relied on to enhance the feedback control and controlling the treatment systems. So now a little bit about brine. So RO concentrate is a byproduct of purification systems. Any purification system that uses RO concentrate, RO membranes would produce RO concentrate. And you cannot just discharge this to a body of water without first modeling and treating and a bunch of other things that need, would meet the regulations. So in the Bay Area, it is especially challenging because we are really landlocked and we cannot just discharge to the bay because the bay has a very low capacity of flushing, unlike Southern California where they can just discharge to the deep ocean. So it's a bit challenging for us here. We started looking at various options for RO concentrate management. So the program that we embarked upon, it started about 5 years ago. Many stakeholders, we hired lots of consultants to assist us, and we looked at 150 plus options to manage RO concentrate from purification facilities, and finally it trickled down to a handful. The current status for managing brine or RO concentrate is that you could blend it with residual waters that come from POTWs or wastewater treatment plants and discharge it to the bay. Because brine or RO concentrate is not something that you would add anything to it. It's the same contaminants that they would have ended up in the bay in the first place anyways. You're just taking the water out of it, you're making it more concentrate. So that initial shock to the local area where you discharge it is the challenge. So you need to address that. And by blending, you can address that, but you need to have enough residual water to blend with to drop that shock factor down to the level that doesn't impact the marine organisms or the environment in general. So that's the major challenge. Therefore, we have to look at also other ways to treat RO concentrate or mitigate the impact of it. So we embarked on a series of pilot studies and desktop evaluations, etc. And one of these areas was looking at nature-based solutions, looking at the nature, how it could treat RO concentrate. Horizontal levee, for example, is one of those. Maybe you have heard of it. There is a big pilot study going on right now at Oral Loma Sanitary Water District where we have joined forces with them and UC Berkeley, Dr. Sedlak's group. Most of you know him. And EBDA, East Bay Discharges Authority, and Orlando Sanitary District to support this project, and we got some grants from the Department of Energy to look at horizontal levee systems and how they can mitigate the impact of RO concentrate. So that has been going on. At the same time, we did another project with the Stanford and UC Berkeley. We looked at engineered treatment cells. There's a picture of that here in the middle. So we looked at shallow waterways, kind of like wetlands, and how photolysis and adding ozone to RO concentrate could mimic the nature and drop the amount of contaminants in RO concentrate. All of these have been successful to a certain extent, but there are always challenges, like, for example, copper and nickel and zinc that exist in the wastewater end up in RO concentrate, and those cannot be easily addressed. We looked at mechanical and chemical systems to remove those contaminants, so capacitive coagulation and other forms of systems, and we have been seeing limited success in those areas. So there is no silver bullet at this point. The picture on the right-hand side at the corner is floating wetlands. That's another nature-based system that we have looked at. We piloted this at our Silicon Valley Advanced Water Purification Center. We looked at removal of copper and nickel. There has been, again, limited success with that. Nevertheless, all these compendiumed together give us a very good picture as where we are going and how we can address the RO concentrate in a larger scale. This is a rendering of our future facility in Palo Alto. So if we build this facility in Palo Alto, the amount of RO concentrate produced would be roughly about 2 mgd. So it's a serious problem to address 2 mgd of RO concentrate when you want to discharge it. Therefore, we did a series of hydrodynamic modeling studies. So the way it works is that you use this very sophisticated model that SFEI has developed, and you set it to run at different concentrations. So we set it to run at 1 mgd, 2 mgd, 3 mgd, etc. So the sweet spot of 2 mgd when we ran it, if we had 2 mgd of RO concentrate discharged to the bay, how would that impact our bay when you discharge it at that point? So the model showed that 2 mgd of RO concentrate can dissipate within about 5 acres of zone, which is called initial zone of dilution. And that initial zone of dilution appeared to be reasonable when we approached and presented that to the regional board. And they kind of felt that it is doable, they felt comfortable with it. And they said, okay, continue on this path and look at not only that, but also look at treatment options. So don't lose the sight of treatment options, because blending works. We are not going to just give you a permit for that, but just go ahead and continue down the path of your studies and evaluations. So in order to make sure that if you dilute and discharge your RO concentrate, you need to do other studies. You need to look at the toxicity. You need to look at other factors. So we are also continuing with that. So we are taking samples of RO concentrate that we generate, and we run rigorous toxicity analysis on them with different species that are in the regulations actually for NPDES permit or discharge of wastewater to the bay. In order to make sure that, because not all RO concentrates are created equally, we need to make sure that the RO concentrate that we are dealing with is water quality matrix specific. So what we do right now is that we transport effluent of wastewater treatment plant from Palo Alto, where our future facility would be located nearby, and would feed into our purification center, because the purification center would take the treated wastewater, purifies it, and puts it into either a reservoir or into the pipe or Los Gatos recharge ponds to serve it, right? So the source of our water is wastewater treatment plant in Palo Alto. So we take that treated wastewater, we simulate that process, and we run it through our RO skid, and we generate RO concentrate that would be produced 6-7 years from now. And then we take that water and we do the testing on it. So that would be the best way of simulating the conditions and finding out whether it's going to be proper to discharge it or not, or what are the contaminants that we're going to be dealing with, etc. So this is a major project we are running right now, and it's ongoing, so it would complete within a year. That should give us lots of information on RO concentrate management for Palo Alto. Last but not the least, public perception is of paramount importance when you want to serve purified water that the source of it is wastewater. So we need to make sure that the public is educated and supports these projects. So bottling the purified water is very important because we can use that as a tool for enhancing public support. When you bring the people to the facility and you show them the great whistles and bells, at the end of the day, you want to show them the product that they can use. And this is where we think we should really invest big. And we have started on this, and we are almost ready to bottle our water. So in order to bottle the water, it's a pretty complex process. You need to run your water through your entire purification train. And at the end of it, you need to run that water through a UV-AOP process, which is ultraviolet advanced oxidation process. So this process would basically zap any remaining contaminants and would produce the water that meets or exceeds the drinking water standards. And it's very safe, and we are confident that when you bottle it and you drink it, it'll be fine. And here's our crew working on this project right now. There is no plutonium-235, it's just purified water, but we are using canisters to make sure that there are no breeding of the spiking chemicals that we use, because we spike the water with certain chemicals like 1,4-dioxane, and then we show the removal, and that's how you validate your process. So our crew is working here, doing the work and doing the initial testing. We submitted our results to the Division of Drinking Water, and everything is a go. Next step is to produce the water within a month or so and then bottle it. When we bottle it, we send it to a bottling facility, and it would be retested again and then sent back to us, and then we can use those bottles to promote our public perception. So with that, I take any questions, and I think I'm on time. Thank you.
Thank you. Any questions, folks?
I have one question.
Sure.
I've heard years ago that the possibility of using the osmotic pressure differential between seawater and fresh water to generate electricity. And I would assume it'd be even greater between concentrate and fresh water. Is there any type of speculation, possibility of doing energy generation, electricity?
So yes, you're correct in that the RO concentrate or brine that is produced from seawater or desalination processes has a higher osmotic pressure, because the TDS in brine is roughly about 75,000 milligram per liter. That's for regular desalination of seawater or ocean water. For purified water, the TDS that comes in is roughly about 800 to 1,000. So the RO concentrate multiplies that by, so the RO membrane multiplies that by a factor of 6. So you end up getting a brine that is roughly about 4,000 milligram per liter. So for that amount of osmotic pressure, you cannot gain much, unless you do recirculation of the brine. And some facilities do that, but those are mostly industrial facilities. So they are not really concerned about energy consumption. They are more concerned about the less waste they produce for handling it at a cheaper, expenditure towards the end. So at this point, there is no energy recovery from osmotic pressure for purification centers. However, there are devices that we would be looking at when we are designing our future facilities for energy recovery, and those come for the high pressure that you use for pushing the water into the RO membrane, because you need like roughly about 300 or 250 psi to push the water through the RO membrane. So that